Alright, so our topic for today is simple harmonic motion. So we'll consider a mass in a horizontal spring. There's a restoring force here from the spring. That force equals minus kx. The reason for the minus just has to do with direction. If you displace the mass to the negative side, the force returns it back towards the positive side. So our force equation, the net force is minus kx. That's got to equal ma. We divide both sides by mass, and you get the acceleration, which is the second derivative of position equals minus k over m times x. So that's a differential equation, and we're looking for the function x that satisfies it. Now, we can just take this position-dependent acceleration and we can integrate it using our integrating factor and then solve for the velocity. But to solve for the position directly, we need to know this function x. You take its second derivative, it equals itself times a constant. Well, that, of course, could be a cosine or a sine function. Let's work with the cosine function and show that that works. So if you take the derivative of a cos omega t, you're going to get derivative of cosines minus sine. Then you need to multiply by the derivative of the argument, which gives you an extra factor of omega. So you get omega times minus a sine omega t. When you do the derivative again, you've got the derivative of negative sine, which is negative cosine. But then you get another factor of omega from doing the derivative of the argument. Multiplied by this one gives you omega squared. So by doing the second derivative of our function, we end up with our original function x multiplied by omega squared. And there is, of course, a minus sign there. So if we compare these two equations, we can see that this omega term, omega squared, has to be k over m in order for this to be a solution. So that means that omega is the root of k over m. Now, a second order differential equation, and it's second order because of the second derivative here, has two independent solutions. So for a general solution of the problem, we actually have to take a sum of the sine solution and the cosine solution. Now, we just showed that the cosine works. You can equally well show that the sine will work as well. Now, there's two constants here, d1 and d2, and those two constants are to be set depending on the initial condition, where the particle is and how fast it's moving in the initial state. This can also be written in the form a cosine omega t plus delta, and you have an assignment to show that these two forms are equivalent, provided that the amplitude and the initial phase angle are given by these two expressions. Now we'll work with this second form. And if that's the position function, if we differentiate it, well, again, the derivative of cosine is negative sine. You will pick up an extra factor of omega by differentiating the inside. And then omega t plus delta sine. You get this function here for the velocity of the particle as a function of time. Now, we will remind you that because the spring force is a conservative force, that there exists a potential energy function. That function is 1/2 kx squared. And in the absence of energy, mechanical energy will be conserved. So the sum of the kinetic and potential energy should be a constant. So using the position and velocity functions, which are here and here, your task is to work out the total mechanical energy and show that it equals 1/2 kx squared. So show that it is indeed a constant. All right, a couple of simple harmonic motion problems for review. So we take a 200 gram mass, it's moving in harmonic motion, frictionless surface, it's attached to a K is 20 spring. At time 0, the mass is 30 centimeters right of equilibrium, and it's at rest. So we let it go. Well, if you let it go, it's obviously going to be pulled back towards equilibrium by the restoring force. Then it'll slow down and stop, and then it'll come back to this side, and so on and so on and so on. If there's no friction or no dissipation, it'll go from plus 0.3 on this side over here to minus 0.3 on this side. So the amplitude we can get by inspection is just 0.3. Now, the rate of vibration is also called the circular frequency omega, is given by the root of k over m. In this case, the k constant is 20, and the mass is 200 grams, or 0.2 kilograms. So we get 20 divided by 0.2, which should be 100. The root of 100 should be 10 radians per second, and the amplitude's 0.3 meters. So that we've got our amplitude, we've got our initial phase, our rate of vibration. We just need our initial phase delta, because standard form, remember, is A cos omega t plus delta. Well, at time 0, the position is 0.3. So if we put time 0 in here, that term just disappears, and you get cos delta. If you put 0.3 on this side and 0.3 on this side, you end up with the equation, and I'll have to write it down here. 0.3 is 0.3 cos of delta. Now, typically, cosine equations like this have an infinite number of solutions and feature 2 solutions in the unit circle. But because 0.3 over 0.3 is 1, there's only one answer to the inverse cosine of 1. It's actually 0. So we get for our position function as a function of time, we get and I'm just trying to make a bit of room here. All of this stuff here tended to go down here. There we go. This stuff too. Not that it's a big deal, but oh, that's frustrating. Come on. So we've solved this now. Somehow the 1 disappeared. The 1 disappeared. We'll put it back here. Oh, that is so irritating. All right, we'll just draw it again. So you get 1 equals cos delta. Delta is the inverse cosine of 1 is 0. So we can now write our position as a function of time. It's just 0.3 cosine of 10t. The initial phase angle was 0. Now let's take exactly the same system, but now instead of being at rest at 0.3, it's actually moving right at 0.4 meters per second. Now this means that the mass is actually going to go a little bit further before stopping, and then it'll turn around and go back on the other side, back and forth, back and forth, back and forth in a harmonic motion. So it means that the amplitude isn't 0.3. The easiest way to find the amplitude is using mechanical energy conservation. So initially there's some kinetic and potential energy because the spring's stretched and it's moving. Up here at the end it will stop momentarily, so there will be no more kinetic energy. You'll have a maximum potential energy at the end. So we set up our energy conservation equation. It basically says 1/2 mv initial squared plus 1/2 k x initial squared equals 1/2 k a squared, where a is the amplitude. So the mass is still 0.2. The initial speed is given as 0.4. The spring constant is still 20. The initial stretch is 0.3. And we have to solve this equation here for the amplitude A. Okay, so the amplitude then works out to be 0.302 meters from this equation. The rate of vibration, well, that's still the root of k over m, and that's still the root of 20 over 0.2. That's still 10 radians per second. So next up, the initial. Okay, so our omega value ends up being 10 radians per second. Now we want to find the initial phase. We know so far the value of the amplitude and the rate of vibration. So we know the amplitude is 0.302, and we know that omega is 10. It remains to find the initial phase angle. Well, we can put the time 0 values in, right? At time 0, the mass is at 0.3. If you put in time 0, this whole term is wiped out, and you just end up with cos of delta. So dividing by 0.302 and doing the inverse cosine, we can get a value for delta. Now, this gives 0.133 radians, but of course with cosine on the unit circle, there's more than one answer. Cosine's positive both in quadrants 1, right here, that's the one that our calculator just gave us, and also in quadrant 4. Which of those should we pick? Well, on the diagram, the object, the mass starts off moving to the right in the positive direction. So we need to see which of these has a positive velocity. Well, it's a negative sine function. Negative sine function will be positive in quadrant 4. The quadrant 4 answer is 2 pi minus 0.133 radians. That is 6.15 radians. And if we were to, at time 0, put 6.15 radians in here, the sine function would be negative, multiplied by this negative in front would end up with a positive velocity. So that's the correct value of initial phase for this problem, not the 0.133, but instead the 6.15, and we can write our position function then as 0.302 cosine 10t plus 6.15 radians. That's really a review from Physics 1120. So we're now going to work at writing this equation of motion in a different form. We'll start off with the differential equation. D squared x dt squared is minus k over mx, and we'll use the omega constant. This is minus omega squared x. The minus omega squared x will bring over to this side, so it'll be plus omega squared x equals 0. We'll introduce the complex number I, which is the square root of negative 1. Now I squared is negative 1, so I can just put in two negative 1s here. Negative I squared, negative 1, positive 1, and I've got the same equation that I had earlier. The reason I do this is that this now factors as a difference of squares, right? This is a squared minus b squared times x. That's going to be a plus b, a minus b times x. Now the only way that that can be a 0 function for every value of x is if the brackets themselves identically are 0 when they act on x. Let's focus on this first bracket. If this is to be 0, then I can just expand this operator and get dx dt plus I omega x is 0. Then I will take the I omega x to the other side. It'll become minus I omega x. And then I'll separate the variables. I'll bring the x down here to join the dx. I'll take the dt up there to join the I omega. So I end up with this equation here, dx over x is minus I omega dt, which I then integrate. So this is going to be integrated from some initial to some final position. This side will be integrated from some initial time, which will make 0, up to some final time, t. Now, the integral of dx over x is just ln x, but then you substitute the upper and subtract the lower limit, but then you use the log property, which simply says this is going to be the log of x over x naught. On this side, the integral is simple. It's just I omega t. Now, we're going to raise both of these to the power of e. We're going to exponentiate both sides. E undoes the log function. You end up with x over x naught. On this side, you get e to the minus I omega t. But then you cross multiply the x naught, realize that it's just a constant, and so you multiply all of this by some constant. So what we're seeing here is that the solution to the differential equation can also be written as an e function, but an e function with a complex exponent. Let's just prove that in another way. We'll go back to our differential equation and just substitute in e to the alpha t. So we're going to take the second derivative then of an e to the alpha t function. Well, each time derivative is just going to give us the function itself times alpha. So one derivative is alpha e to the alpha t. The second derivative is alpha squared e to the alpha t. And if this is to be a solution to the differential equation, the left-hand side has to equal the right-hand side, and the right-hand side is just minus k over m times the function e to the alpha t. So for this to be a solution, alpha squared has got to equal negative k over m. So when you take the square root for alpha, it's got to be the root of negative k over m, which we can write as the root of negative 1 times the root of k over m. Root of negative 1 is I, root of k over m is omega. So once again, we see that the solution can be written in the form e to the plus or minus I omega t. The reason we want to do this is that this form of the equation of motion enables us to more quickly solve the differential equations that are to come later. Now, how can we have a position given by a complex number? Well, it's understood when we do this that we're using the exponential to make the solutions easier. But of course, if we ever want to graph the motion or get real values for the motion, we're just going to take the real part of that complex exponential. In order to find that, it's helpful to know Euler's theorem, which says e to the I theta is cos theta plus I sine theta. You're going to prove that here using Taylor's series. A final idea for today is we're going to return back to mechanical energy conservation. Kinetic plus potential, 1/2 mv squared plus 1/2 kx squared is a constant. One way we can visualize that motion is on a position velocity plot. This is known as a phase space plot. So we're going to plot position on the x-axis and velocity on the y-axis. Now, because 1/2 mv squared plus 1/2 kx squared is a constant, the graph is going to have a standard form. You see, if it was x squared plus v squared equals a constant, and as long as the constant's positive, this would be the equation of the circle. But the coefficient of v squared and of x squared isn't necessarily the same. And if those coefficients are different, then it isn't a circle, it's actually an ellipse. Now, you'd need to know the relative values of m and k to know whether it's squashed this way with its major axis vertical or its major axis horizontal. So we can't a priori say which way the ellipse is squashed, but we can say that it will be an ellipse. Now, it's possible, of course, to have values of m and k if they're equal such that it is circular, but in general it will be elliptical. Let's imagine, and we'll just do an example here, that we have a mass starting at rest at x is plus a. So the velocity axis is 0, the position axis it's plus a. We've got to be out here at this point right here initially. Now, as you let this thing go, the position value is going to go to 0. That means it's somewhere here on the axis. At this point, the velocity is going to be to the left and negative. That means we're actually down here on the velocity axis. The mass is then going to slow down and stop. So the velocity will again go to 0, this time at a negative position value. So the motion is representable in this form here. We see that we're running along an ellipse in phase space, and the position and velocity values are changing in this way. Now, if that is an ideal spring, then it'll come back to the same positive A position, and you'll just go around and around and around and around on this ellipse in phase space repeatedly, over and over again. Let's make a numerical example here for you to do as part of your assignment for next class.